Hi, this is VishnuVandana Pyatla, and I'm going to discuss about a research paper on NetPanel, which is the traffic measurement of Exchange Online Service. So the components of the cloud application will be generating large volumes of data of the network constantly, which will be leading to large cost of the cloud applications. To overcome this situation, NetPanel has been introduced. NetPanel is a special tool that is developed by Microsoft for their cloud service, which is Exchange Online. This Exchange Online will help us to understand and manage the huge amount of network traffic that is generated by thousands of components in the cloud application. By figuring out which components are contributing the most to traffic, we'll be able to find ways to reduce the costs. So this net panel will be combining data from different sources to measure the traffic at the level of individual components by making it very much easier for each service of the team to take ownership of their part. By using NetPanel, Microsoft gained valuable insights about the traffic and saved millions of dollars in network resources. And here, the best part is that by running NetPanel doesn't require much computer power, so it also won't affect the performance of their service or EXO, which is Exchange Online at all. And for the introduction, let's just imagine a huge cloud application, which is called Exchange Online, which has thousands of parts working together on many other servers. And here, each part is like a team which is responsible for a specific task. These parts send a lot of data across the internet, which will be costing a lot of money. And sometimes there's a situation that these problems in one part can cause a flood of data, causing issues with the customers. And the existing monitors can't match all the problems that are related to data traffic, leading to unnecessary expenses. So Microsoft has created NetPanel, which is a very clever tool that tracks the data flow of each part to find the owners of the data traffic. It also combines different data sources to measure the traffic in a way that not too resource intensive. By using the NetPanel, Microsoft has also saved millions of dollars by optimizing their data traffic. The tools here run smoothly on their servers, causing almost no impact on performance. And here in this presentation, I'll be explaining how NetPanel works, the challenges that it solves, and how the NetPanel has helped Microsoft to manage their cloud applications more effectively. And the NetPanel will also be allowing the data questioning for a long time, which is not having to compromise the performance. And it has an ability to operate with just a minimum of impact on the servers of production by using less than 1% of CPU and input-output disk. And there are some of the considerations for the designer of NetPanel, and they are: the first one is measurement at the component level, and the second one is the daily data size should be of GB level, and the production environment should run under the very strict resources. Let us discuss the background of all this topic. So Exchange Online, EXO, is a master cloud application. First of all, let's discuss about EXO service traffic. This EXO with servers all over the world comes in three types. They are FE, BE, and AD. So each of these will be serving different functions, like FE servers handle customer requests, AD servers store user data, and BE servers handle emails and also mailboxes. The EXO servers, they talk to each other to provide services to the customers. And here we are interested in the WAN traffic, the data that goes through the internet between the servers. And here this traffic is the most expensive part of running EXO. There are basically two types of WAN traffic, that is internet traffic, which is in between servers and user devices, and internal long-haul traffic, which is in between the EXO servers by themselves. In the internet long-haul traffic is further divided into tier 0, which has higher priority, and tier 1, which has very lower priority. And managing this traffic is essential to keep costs down and ensure smooth operation. In our presentation here, I'll be explaining and exploring how different types of traffic impact EXO and how we'll be optimizing it to save the money and provide a very better experience to the users. And here we have is the EXO traffic overview request flow. And let us understand this with a very simple example. In this scenario, we have 6 locations like location A, location B here, location C, location D, location E, and location F. And the Alice is at location A, Bob is at location F. So in this scenario, let's just imagine that Bob here at location F is sending an email to Alice at location A using the desktop client. So Alice reads her email using a web client. The email goes from Bob's location F, which is in here, to Alice's mailbox in another location, which is location E. The mailbox, this one, is also replicated in third location here at location D for the sake of backup. And to read the email, Alice's web client first contacts the front end. Here it is, the front end, which is at location B. This step uses internet traffic because the FE server communicates with an external client, which is Alice's web client outside of the Microsoft. And the FE server then talks to an Active Directory AD server in location C here. And this is done to find out which back-end server hosts Alice's mailbox. And this step and the next one, which is FE server querying the BE server in location D, involve tier 0 traffic because the servers are in different locations. And after figuring out where the mailbox is hosted, that is at location D, the FE server in location B here forwards Alice's request to another FE server in location D, which is here, and that this FE server transfers the request to the BE server in location D, like this. The response from the mailbox travels back to Alice following the same path that we have discussed. This part of the process involves tier 0 traffic between FE servers and metro traffic between FE and BE servers in the same location. The replication traffic, which is here a blue dotted line, is called tier 1 traffic. It also includes the background traffic for the things like the data replication for backup, mailbox migrations, or log uploads. And it is essential to use application logs to measure traffic between FE servers accurately because they capture long-distance traffic. And BE servers in the same location can't differentiate requests originating from the other locations. So the application logs are basically very necessary for the detailed measurements. So in total, like this scenario illustrates the different types of traffic in Microsoft Exchange Online Service. And understanding these the traffic patterns helps optimize the network resources and reduces the cost effectively. And let's now understand the EXO traffic generation. EXO, or the Exchange Online, is a system that facilitates the communication of emails between servers. This communication involves like various types of traffic, which also includes tier 0, internet traffic, and metro traffic. Tier 0 traffic likely refers to critical communication processes that are essential for the functioning of the system. Internet traffic pertains to emails being sent or received from external sources or the network, while the metro traffic could involve emails being exchanged in between them within a local or metropolitan network. And at the tier 1 level, tasks such as background activities, replication, and migrations take place to ensure there is a smooth email flow and there is a good system maintenance. To also improve the traffic flow at a more granular level, measuring the traffic at the component level becomes crucial. However, to obtain these highly detailed insights into the traffic, the application logs will be playing a very important role. These logs will provide us the important measurements and data about the email communication patterns and also helping to understand and also operate fine tune the system for the optimal performance and also reliability. Now let's understand the measurements of traffic. In our data centers, basically, we have two types of measuring network traffic. The first one is on router and the second one is on server methods. On router measurements use flow monitoring, which groups packets into flows based on their source and destination addresses, ports, and protocol. And this all of this data has been sent to a centralized storage. On the other hand, on-server measurements use tools like TCP dump for Linux and even tracking for Windows, which is ETW, to monitor the traffic usage of all of the processes on a sys server. Additionally, application logs are also used for debugging processes and to provide the information about some of the very specific requests like timestamps, serving components, server names, latency, request, and response content size. Here, each method has its own strengths, like IPFIX, it covers IP, port, DSCP, which is a tag that is used for traffic priority. ETW can measure processes and application logs contain detailed information about requests and responses. In order to get a complete picture at the component level, we need to combine data from IPFIX, ETW, and application logs because they will be providing us different pieces of the puzzle. So in this manner, we'll be better understanding the traffic and optimize our cloud services effectively. Now let us know if there are any design considerations for the NetPanel, and yes, there are some of the design considerations. Because NetPanel is a system which is designed to measure and analyze the network traffic in a large-scale environment like EXO, which runs on hundreds of thousands of machines with different server roles. And it has mainly three goals. So the first one is the result should be at the component level, which means that the system needs to provide the results at the level of individual components as each component is owned by an engineering team and they need to optimize its cost. However, existing measurement methods can't support this level of clarity, and the NetPanel overcomes this challenge by using three of the data sources. Those are IPFIX, ETW, and application logs to map components to their respective traffic flow. And the second one, or the second goal, is that there should be a very small daily measurement result size, which means that the EXO generates massive amounts of data from day to day, and the engineers need to analyze it over long time intervals for the meaningful insights. So to make all of these analyses to be important and to be feasible, NetPanel compresses and limits the data size to a few gigabytes per day so that it will enable efficient queries and resource usage. The data that is used for analysis should cover continuous time intervals of several weeks so that it will be able to account for the dynamic nature of the network traffic. And the third goal is that it should be resource efficient collector in production environment, which means that the data collected in the production environment must run with strict resource restrictions to reserve resources for user requests. And here, NetPanel achieves this by focusing on recording traffic data from the CHAP-K ports, reducing log size, computation resources, and disk input-output throughput. This approach also allows the system to comply with the resource limits set for the production environment. So the NetPanel's design goals are to provide component level results, maintain small daily measurement result sizes, and ensure efficient resource usage in the production environment. To achieve these goals, it leverages multiple data sources, compresses data, and focuses on the most relevant traffic information. And here you can see the picture, which is a description of all geographical regions that have fluctuations in between daytime and nighttime but follow a very similar weekly pattern. And here the values could be half the peak values. And as we can see here, the x-axis has the dates and the y-axis has the normalized traffic. The red graph shows the North America and the blue graph shows the Europe. And here the figure shows the traffic variation in EXO over a time interval of more than 1 week in North America and Europe. The traffic volume highly aligns with other user activities with more traffic during working hours and much less at night and on weekends. The values are nearly half of the peak values here as you can see, and the large fluctuation rate is likely to override the traffic change that is introduced by a new feature if we make queries only over a short interval of a few hours. And here you can see another graph for different components having various different traffic patterns. And on the x-axis, we have the date as the same as the above picture. On the y-axis, we have normalized traffic. And component 1 is explained in the yellow colored graph, and the component 2 is represented with green color. So here we see the different components having different traffic patterns, and we can also see the traffic patterns of two components in the figure having the component 1 fluctuating greatly while that of component 2 is like mostly stable. And here's a picture of the overview of the NetPanel architecture. And here we have the data sources, data validation, data processing, result database, consumers. And in data sources, we have IPFIX data, ETW data, application logs, management data. And in consumers, we have monitor, web UI. And in the result database, we have top K port, source port, destination port, process, component, metro, and validation. And in data validation, we have machine pair selection, data filter, and in data processing, we have feature translation, data split, and data aggregation. So here in the data sources, the first one that is IPFIX data, this provides information about the network traffic flow. And the ETW data, it gives us valuable insights into a system, events, and also its performances. The third one, application logs. So these logs contain important application-specific information. And the last one, management data, this helps us in monitoring and managing the system. So the basic main goal of the NetPanel is to identify and to monitor the latest top K ports. These are the most significant ports in the network. We store the results in a database which includes information about these top K ports along with their associated source port, destination port, process, component, and location, which is a metro. And this data is used for validation purposes as well. And here we have two types of consumers in NetPanel as we have discussed. So the first one, monitor, is responsible for continuously monitoring the network and collecting data from various sources. And the web UI provides a user-friendly interface to view and analyze the monitored data. And the data processing in NetPanel involves several steps, like the feature translation is used to convert the data, here this one, from different sources into a common format for better analysis. And the data split here, it is a large data set are divided into smaller manageable chunks for efficient processing. And the data aggregation, we combine the relevant data to get a more comprehensive view of the network traffic. So just to conclude this, we can say that NetPanel is an architecture that is designed to collect, process, and analyze the network data efficiently. It also identifies the most important ports which stores the results in a database. And here we have the system design, just as I discussed above. We have data sources, validation, data processing, and everything. And here are all of the names of them. And here we can see a graph and also a pie chart. And the graph says the many ports will be dominating the traffic in total, and the pie chart, it says the many components will be dominating the traffic of a top port. So from the source port and the destination port tables, we have observed that several top ports contribute to most traffic usage, and the figure here shows the traffic of total traffic generated by the top 10 ports over like half a month period. The lowest value during this period is 94.8%. So this result confirms that the top key ports will filter algorithm could cover at least 94% of the total traffic for ETW collector when k is equals to 10. And along with this, the list of top ports remain unchanged during our observation here. So our observation here supports us to use the latest K ports obtained as a filter for the ETW collectors. The concentrated traffic here, the distribution at a few top ports saves us a lot of traffic optimization work. And here we can also focus on a small number of ports when we want to reduce network traffic costs. We engage the partner teams that use these ports instead of calling every team in EXO. And here we have studied a lot of case studies. So in these case studies, we can see how we use NetPanel to refine the WAN traffic for EXO. And these 4 cases where we use NetPanel for are the first one is service traffic optimization, the second one is legacy traffic discovery, and the third one is anomaly traffic burst detection, and the fourth one is WAN feature validation. So let's discuss one after one. So the first one is service traffic optimization. In this case, we introduce how we use NetPanel to identify suboptimal traffic and optimize the utilization of network resources. Here, the NetPanel provides long-term data visualization. So this makes it easy for the application to identify its major traffic contributor. And after engaging the OIM team, it is easy to make a conclusion on whether the traffic is necessary. During our investigation of the traffic composition of EXO, we have discovered that the tier 0 traffic from our BE servers to port A on FE servers is too large because EXO has optimized the internal service endpoint to serve requests with the nearest FE server. We expect that there should be little tier 0 traffic from BE to FE. And here, the traffic change is shown, and the traffic with destination port A decreased by 20% of the change. And before the NetPanel, it relied heavily on code reviews to prevent such cases, and this manual approach was likely to lead to omissions. And let's discuss the legacy traffic discovery. So this is another case where NetPanel helped discover legacy traffic and its code source. As the system grows, the source code becomes overwhelming. The work to remove the outdated settings and services is really necessary. But it turns out that it is hard to discover legacies while do not break anything. We also have figured out here that there was one component on BE machines that was sending traffic to certificate authorities to validate some certificates that had been retired. We have also started from the continuous and expected high traffic volume from port C in the NetPanel source port table. And here we can see that the traffic from port C is 42% of the traffic from port D. And the traffic of both ports during the fix is to be shown here. And after the removal, the traffic with source port C dropped to lower than like 10%, like you can see it here, it is 4%. This fix led to savings of inbound capacity in the GBPS for Microsoft. And now let's discuss the anomaly traffic bus detection, which is the changing accidentally the compression algorithm to older version quadruple peak traffic. So this case shows that how we leverage NetPanel to detect an anomaly traffic burst caused by configuration error. Some configuration errors at the application level may cause abnormal network behavior. Like for example, A configuration error may cause the component to keep sending requests to an endpoint and thus lead to traffic burst. And these bugs are hard to detect unless the affected machines get so hot and break critical services. And let's discuss the case study 4, which is WAN feature validation, which discusses about the new device which doesn't support existing feature well, traffic priority out of expectation. So this section basically introduces how NetPanel triggers a feature validation on newly deployed devices. When a new type of device starts to be deployed in the network, it may miss some functionality. Regional WAN aggregator, which is RWA, it is a kind of core router recently added to the Azure network that sits on top of the data centers, and also it is responsible to connect the data center network to the backbone WAN. In this case, we can also see that the newly deployed RWA devices do not also support the QoS policy. They also ignore the DSCP tag and treat all traffic with tier 0 priority. Now let's discuss about the evaluation here, the overhead in the environment of production. So here we evaluated the overhead of NetPanel into like two categories, that is overhead inside and outside the production environment. This production environment serves customer requests and also has strong restrictions on resource consumption, while the restrictions on overhead outside the production environment are more relaxed. So here, this figure shows the evaluation of NetPanel's performance in the production environment, where it serves the customer request with strict resource restrictions. The focus here is basically on measuring the overhead that is introduced by the ETW collector, which is responsible for gathering the network data. So when only essential services are running on the server, the CPU and disk input-output usage are relatively low. But when the raw ETW, that is event tracing for Windows, is enabled to collect network data, it significantly increases the CPU and disk input-output consumption. In fact, it utilizes 25 times more CPU and 77 times more disk input-output when compared to ETW is disabled. But here, however, when NetPanel is deployed on production machines, it efficiently manages the resource consumption by only retaining data from the top ports as explained in section. And as a result, the rise in total CPU and disk input-output usage is like less than 1%. So this means that the NetPanel saves a very significant amount of resources by reducing the CPU usage by 99.1% and disk input-output by 99.7% when compared to using the raw ETW. And to put this in total in simple terms, NetPanel optimizes the resource usage in the production environment by collecting only essential network data, which results in minimal impact on CPU and disk input-output while still providing valuable insights for monitoring and analyzing the network traffic. And here we discuss about the overhead that is outside of the environment of production, and it takes like 10 of seconds to query 60 days of data. This section also discusses the overhead of running NetPanel outside of the production environment. And it basically includes two main aspects. The first one is data storage and computation, and the second one is data storage overhead. And now let's discuss about the first one, that is data storage overhead in just brief. So NetPanel reduced the data size significantly when storing the results when compared to the original data. For IPFIX data, the result size is only 0.00361% of the original size. For ETW data, it is 0.00076%, and for application logs, it is 0.00003%. This means that the daily result sizes are relatively small, close to each other, and measured in gigabytes. And let's come to computation overhead really quick. So in computation overhead, the processing time for each data source is reasonable by given in the tight resource restrictions, with IPFIX taking 1.1 hours, by ETW taking 1.6 hours, and application logs taking 6.8 hours daily. Although it may seem long, the trade-off is acceptable because NetPanel aims to support cost reduction in the long run, and a delay of a few hours is manageable. So the NetPanel will be efficiently managing the data storage and computation by ensuring that the system responds quickly to user queries while keeping the resource consumption low. This allows NetPanel to support cost optimization and network traffic analysis effectively. And to conclude the project in whole, in cloud applications like EXO, the network traffic generated by various components can be massive and resource intensive. So, to optimize its cost, it is essential to understand the composition of this traffic at a detailed level. NetPanel also addresses this need by analyzing network traffic at the component level while keeping the cost low. But one major challenge here is dealing with the huge amount of measurement data. And to overcome this challenge, NetPanel employs several techniques to reduce the data size without compromising the accuracy of the analysis. By doing all of this process, it provides valuable insights into network traffic by helping to optimize the cost for system developed by different teams. So if we come to the real world case of the NetPanel has been successfully applied by resulting in saving millions of dollars per year in cloud application costs. The experience that is gained from designing and operating NetPanel can be beneficial for other cloud applications that are seeking to measure and reduce their network traffic effectively. So, the NetPanel is a system that analyzes network traffic at the component level in cloud applications. It also manages to do so while keeping costs low and dealing with large volumes of data. And the insights that are gained from using NetPanel have proven to be valuable in optimizing costs and also being helpful for other cloud applications as well. Thank you so much.